Question 16, page 3. This question refers to the following diagram of a 0.5 volts, you don't know whether it's plus or minus. There's a charge of 0.05 microcoulomb, we don't know whether they're plus or minus. A small sphere carrying a positive charge of 0.5 by 10 to the minus 6 coulombs is placed in the electric field between parallel plates. The electric force is arranged exactly opposite to the force of G. So W equals mg, and therefore we have F E equals EQ. A small positive charge. So which plate must be negative? The top plate. Top. They have to be negative to lift the charge upwards. Let's get the shape of the electric field lines between the plates. We have to do this with a ruler, and I'm doing it much larger here. And what you have to do is say equispaced. You may also give a detail here. They hit the plate at 90 degrees. Now you have to say that because the examiner, even though you may draw it carefully, the examiner may not believe it. A force has got a mass of 1.2 by 10 to the minus 6 kilograms. What is the strength of the field? We have it from here, EQ equals mg. So we have E equals mg on Q. I'm just writing it fairly large over here. Equals 1.02 E minus 6. 9.8 on Q, which is 0.5 E minus 6. So that's approximately, I haven't brought the calculator here, volts per meter or Newton per coulomb. Okay, the light bulb when viewed at a distance of 0.5 meters has an intensity of 0.32 watts per meter squared. Calculate the distance the light bulb would need to be weighed to have an intensity of 0.5. Okay, I always like the inverse square law written like this, although examiners may not like it this way. It's intensity R squared equals of 1, intensity 2, R squared 2. Now calculate the distance the light bulb would be needed. Okay, so R1 equals the square root of I2 R2 squared R1 all squared. Let's see if we can get a light bulb. Sorry, a calculator. I believe we'll enter that side. Bit embarrassing, I don't have my calculator for this one. But putting the numbers in. 0.32 dot 25 on 0.1 half of a half, 25. Oh god, well let's see. 0.25 on is 100, so that's 10 outside the brackets. Oh well, that's 100. Oh, that's 100 is the square root of 32, which is 2 the square root of 6, whatever that number is. Now we're coming down here, so remember that's 20, automatically that's 80, and if that's 53, that's 27, no 20, sorry 37. That's from the normal and the rays going this way. Here, sorry. Simon wishes to determine the refractive index of glass, so we know that's approximately 1.5. He sets up an experiment as shown above diagram. He measures with the projector, this person finds an angle between the glass prism, that and that. The limitations to its nearest degree. Calculate the refractive index of the glass. Well, would state that equals 1. So in glass on in air equals sine air, which is 80 degrees, on sine 37 degrees. So sine I on sine R equals N1 on N2 equals sine I on sine R.